The group of quantum physics and devices of Professor Carlo Sirtori is part of the Laboratoire Matériaux et Phénomènes Quantiques of the University Paris-Diderot. Our research activity focuses on the investigation of infrared optoelectronic devices with new functionality and on the study of interesting effects related to electronic transport, optical properties, and light-matter interaction. We work on the conception, realization, and characterization of low-dimensional structures, providing artificial effective confinement for electrons and photons. Intersubband devices based on transition between confined state of semiconductor quantum wells are at the heart of our activity.
In this paper, we investigate the process of light emission from collective excitations in semiconductor quantum wells with very high doping. These excitations are called multi-subband plasmon, and they consist in a collective oscillation of the electron gas confined in the well. This oscillation creates a huge dipole, and that dipole is very strongly coupled with light. In this work, we study different optoelectronic devices with different numbers of such quantum wells. We show that the process of light emission must be considered as a collective phenomenon involving simultaneously the plasmons located in all the different wells of the structure. And this collective character has two main consequences: superradiance, that is, an increase of the emission rate with the number of wells, and the cooperative Lamb shift, which is a shift of the emission frequency due to emission and absorption of virtual photons.
We start from the conception and the design of the semiconductor heterostructure. A heavily doped gallium indium arsenide quantum well is a proper system to show the spontaneous emission of intersubband plasmon. Thanks to our collaboration with the Laboratoire de Photonique et Nanostructure, we are able to fabricate such a device by inserting the active region into a transistor-like geometry in order to electrically pump the structure. Thermal emission experiments are performed at room temperature by applying an in-plane modulated current. To collect the emitted radiation, we first process the sample with a mechanically polished facet, and then focus thermal emission on the optical axis of a Fourier transform infrared spectrometer. The output signal is measured with a mercury cadmium telluride detector cooled at 77 K. In order to show the angular dependence of the incandescent collective excitation, we mount the sample on a support that enables rotation with respect to the normal to the surface. We compare the emission spectra obtained for two samples with 1 or 6 identical quantum wells. The results strongly depend on the number of wells, and in the 6th well sample we observe a strong broadening of the emission peak that is characteristic of the superradiant increase of the emission rate, as well as a blue shift of the emission frequency that corresponds to the cooperative Lamb shift.
To support this interpretation, we developed a theoretical description based on quantum Langevin equations. In this model, we consider the coupling between the plasmons and two baths. The bath of the photons of the surrounding environment and an electronic bath that accounts for both the thermal excitation and the non-radiative decay of the plasmons. The light-matter interaction is treated in a quantitative way and within a fully quantum framework. This provides an accurate description of both the broadening and the shift of the emission resonance, and this confirms that they originate from superradiance and cooperative Lamb shift respectively.